Here at the wind tunnel, we are going to measure the drag of several different shapes. One of them is streamlined. All these measurements will be made at exactly the same airspeed. We begin by mounting on the arm an airfoil in its proper position, with the rounded nose facing the airstream. When I start the blower, I am going to increase the speed until the drag force acting on the airfoil reaches 1 unit on the scale. As you saw, the drag force was 1 unit when the airspeed reached 210 miles per hour. In the experiments to follow, we will reproduce this same airspeed of 210 miles per hour while we measure the drag to compare with a figure of unity. I am now turning over the airfoil into its wrong position, with the sharp edge facing the airflow and with a rounded edge at the rear. I haven't changed the controls, so that when we start the blower, we should expect the same speed as before. We did reach the same speed of 210 miles per hour, and we saw that the scale read 2.6. The drag of the airfoil the wrong way around, therefore, is about 2.5 times greater than the drag when it is the right way around. Now let's take the airfoil off altogether so that we measure the drag of the rectangular support alone. Even though the cross-sectional area of this rectangular support is very much less than that of the airfoil, its drag is about 4 times as large. This is a circular rod, the diameter of which is exactly the same as the maximum thickness of the airfoil. So you might think of the airfoil as being the rod with an extended nose and a sharpened tail. All right, we're ready to go again. The speed once again reached 210 miles per hour, and you saw from the scale that the drag on the round rod was more than 9 times as great as the drag on the airfoil, having the same maximum thickness. This series of 4 experiments illustrates in a most striking way the value of streamlining in reducing the drag. Perhaps you remember that in the early days of airplanes, particularly when biplanes were used, that wire struts were used to stiffen and strengthen the structure of the airplane. You can well imagine from these experiments how much this added to the drag. To illustrate this point, we have prepared this frame which holds taut a wire whose diameter is about 1/10 the maximum thickness of the airfoil. I'll just slip this frame in place. Before we begin, I'd like you to notice that this frame is well clear of the jet, so that we will measure only the drag of the wire. the wire is just about the same as the drag of the airfoil. The properly streamlined strut can be 10 times thicker than a wire and yet have no more drag. So you see that there is good reason for this change in aircraft design. But how can we explain the results of these extraordinary streamlining experiments? The secret lies in an understanding of the boundary layer, particularly that when a boundary layer is required to flow from a region of low pressure to a region of high pressure, it may be stalled and come to rest, thus disrupting the entire flow. Let us think about the flow past this streamlined airfoil. To begin with, suppose that the fluid has no viscosity at all and that it can slip past the surface. Then the particle trajectories, the streamlines, are as shown in this sketch. Consider the central streamline, which splits at the nose, runs around the airfoil, and rejoins at the tail. A more advanced analysis than is possible in this film shows that the particle speeds at different points along the streamline are proportional to the lengths of these arrows. Beginning with a free stream speed far upstream, a fluid particle decelerates to zero speed at the nose. We call this a stagnation point. Then it accelerates to its maximum speed at about the position of maximum thickness of the airfoil. Then it decelerates to another stagnation point at the tail. And finally, it accelerates to the same free stream speed far downstream. Now, how does the pressure change along this same streamline? As the fluid particle approaches the nose, it decelerates. Since viscous forces are by assumption absent, this deceleration can only be produced by the pressure forces on the rearward and the forward faces of the particle. Here is an enlargement of our fluid particle. In a deceleration, the net force is against the flow. The pressure on the forward face of the particle must therefore be larger than the pressure on the rearward face. This sort of thinking leads us to what is called Bernoulli's law, which may be stated as follows. In a non-viscous flow, a deceleration is accompanied by a rise in pressure along the streamline. Conversely, in an acceleration, there must be a fall in pressure along the streamline. Using Bernoulli's law, we can now work out the pressure distribution for the streamlined airfoil. Far upstream and far downstream, where we have free stream speed, the pressure is atmospheric. At the nose and at the tail, where we have zero speed, we have the highest pressure. And at the shoulder, where the speed is highest, the pressure is lowest. As it travels along the surface of the airfoil from shoulder to tail, while regaining pressure. Now we must worry about how all this is changed when viscosity is present. The velocity at the airfoil surface is then zero. But at very high those numbers, we have only a very thin boundary layer. Only a very thin boundary layer in which viscosity is important. The remainder of the flow behaves as before, in a non-viscous way. The pressure distribution previously established by the main large body of non-viscous flow is, as it were, impressed on the very thin boundary layer of fluid. The particles in the boundary layer must respond to the forces produced by this pressure distribution. Between the nose and the shoulder, a boundary layer particle is pushed along in the right direction by the falling pressure, even though its momentum at the shoulder is less than it would otherwise have been. because of the opposing effect of viscous forces. As it begins its journey from the shoulder to the tail, the boundary layer particle not only starts with a reduced momentum, but must buck both the opposing viscous forces and the decelerating forces now produced by the rising pressure. If the rate of pressure rise is too great, the boundary layer particle may slow to a dead halt. We call this stall, and then get pushed backwards by the higher pressure at the tail. In this flow past the aft end of an object, watch the particles near the wall. Watch again. If stall does occur, we get a flow such as this. The main body of flow separates or lifts from the body and flows around a recirculating region filled with eddies. Some of these ideas may be illustrated in analogy by a marble in a bowl. When the marble starts down the bowl, it speeds up as it approaches the bottom, then decelerates as it rolls up the other side. With no friction, the interchange between potential and kinetic energy would be without loss, and the marble would just make it to the top as its last bit of momentum was used up. But with even the least amount of friction, the marble could not reach the top and would roll back again. A fluid particle in the boundary layer can behave in a similar way, as it first goes down a pressure hill and then up a pressure hill. But fortunately, the analogy of the marble in the bowl is not complete. If it were, there would always be some backflow in the boundary layer, with consequent separation of the main flow. Let's remember that precisely because the boundary layer is moving much more slowly than the external flow, the faster moving outside fluid exerts a viscous force on the boundary layer, which actually assists the boundary layer to continue in the downstream direction. It is then a question of whether this assisting force is sufficiently large to counterbalance the combined opposing forces due to friction at the wall and to the increase of pressure. With a thin body having a long tapered tail, like the airfoil, the rate of pressure rise from shoulder to tail is so moderate that the boundary layer gets nearly all the way to the tail without becoming stalled. The main outside flow is then virtually the same, as though there were no viscosity at all. And the pressure distribution, which is the same as in the non-viscous flow, produces no pressure drag. Now at last we can be more precise about the meaning of streamlining. By definition, a shape is said to be streamlined if there is no boundary layer separation. At high Reynolds number, a streamlined object has no drag due to pressure. Now let's think about unstreamlined objects, like the circular rod or the ball. We call these blunt objects because they do not have long tapered tails. With a blunt object, the pressure rise from shoulder to tail is so sharp that the boundary layer stalls near the shoulder itself. There is then a broad eddying wake, much larger than with a streamlined shape. And the pressure on the rearward part of the body is no longer equal to the pressure on the forward part. It lies somewhere between the low pressure at the shoulder and the high pressure at the nose. The situation then is that the average pressure on the forward half of the body is larger than the average pressure on the rearward half, and there is thus a net pressure drag. With a blunt object, this net pressure drag is usually many times greater than the viscous friction drag. In this smoke flow picture, you can see separation occurring near the shoulder on the ball. Notice here the movement of smoke from the high pressure zone at the tail to the low pressure region at the shoulder. Now, with this streamlined shape, see how the boundary layer flow remains attached to the surface well beyond the shoulder. And notice too how narrow the wake is. In this case, the pressure recovery is almost complete. Thinking back to our comparative experiments, we can see now why the airfoil had less drag in its proper position. When we reversed the airfoil, with the sharp edge facing the wind, the rise in pressure from shoulder to tail was too abrupt. And our other shapes, the rectangular support, the round rod, the wire, all have severe adverse pressure gradients, leading to separated flows and to large pressure drags. But streamlining is not new. Long ago, nature herself perfected shapes of low drag. Look at this view of a trout seen from above. We've outlined its shape. Now, look at this modern low-drag airfoil. Watch. We have seen how strikingly the drag may be decreased by streamlining at high Reynolds number. But earlier we saw that streamlining increases the drag at low Reynolds number. Now we can explain why. At very low Reynolds number, the whole flow behaves in a very viscous way. So there is no such thing as a boundary layer. Here is a little experiment which shows what a difference this makes. I'm going to drop into the column of water a ball coated with dye. The flow separates, as in the smoke flow experiments. Now I am going to drop into the column of glycerin a ball coated with colored glycerin. The flow does not separate, and the fluid next to the surface of the ball flows into a single streamline at the rear. So we see high Reynolds number, separation. Low Reynolds number, no separation. We saw before that separation at high Reynolds number is caused by the special nature of the pressure distribution produced by the main body of non-viscous flow. A falling pressure from the nose to the shoulder, followed by a rising pressure from the shoulder to the tail. Not only falls from the nose to the shoulder, but continues to fall from the shoulder to the tail. This constantly falling pressure pushes along the low momentum fluid near the surface, and so there is no backflow and no separation. The glycerin experiment. Since separation is not now a factor, streamlining does not much change the pressure drag. But streamlining does increase considerably the viscous drag because of the increased surface area over which the frictional stresses act. Thus the total drag is increased by streamlining at low Reynolds number. Well, that clears up one of the paradoxes we saw in the early part of the film. Now for the next. You remember that we observed the drag of the slightly roughened ball at various wind speeds. You recall that at first the drag increased with speed, but at a certain speed, the drag then fell as the speed increased, after which the drag once again increased with speed. This jump from one smooth drag speed curve to a different smooth drag speed curve suggests that we are dealing with two essentially different phenomena. This is correct. Laminar and turbulent boundary layers. The ball is a blunt object, so at high Reynolds number, most of the drag is pressure drag, associated with a relatively low pressure in the separated wake. At relatively low speed, the boundary layer is laminar, and the separation of the boundary layer occurs somewhat upstream of the point of maximum thickness of the ball. This produces a large separated wake where the pressure is low, thus the relatively large pressure drag. Now, if we increase the speed, we have somewhat the same situation as the water flowing out of the faucet at high speed. The boundary layer becomes turbulent. To see why this is important, let's look at the flow in this channel. To begin with, it is laminar. The main flow establishes a low pressure at the shoulder and a higher pressure downstream. The low momentum fluid near the wall is pushed upstream by this pressure difference. Consequently, the main flow separates near the shoulder. When this obstruction is placed in the laminar boundary layer just upstream of the shoulder, it stirs up the flow and changes it to a turbulent boundary layer. See how the turbulent boundary layer remains attached to the wall, reducing considerably the area of separation. When the obstruction is removed, the boundary layer becomes laminar again, and the main flow separates. As compared with the laminar boundary layer, the turbulent boundary layer has a great deal of mixing in it. This creates a momentum exchange, by which the low-speed fluid can borrow momentum from the high-speed fluid. Thus, the turbulent boundary layer can flow farther against an adverse pressure gradient. Returning to our ball, the turbulent boundary layer remains attached beyond the point of maximum thickness. Thus, the area of low pressure on the downstream side is narrower than in the laminar case. Consequently, the pressure drag is less. Let's think now about both components of the drag for the laminar case and the turbulent case. Let this box represent the total drag for the laminar case. With a blunt object, most of the total drag is pressure drag, and only a small fraction is viscous friction drag. But when we have a turbulent layer, the friction drag is greater than for the laminar case. The pressure drag, however, is considerably less because of the reduced area of the wake. The magnitudes are such that the total drag is reduced by the transition from a laminar layer to a turbulent layer. This jump is the result of just such a transition from a laminar flow to a turbulent flow. And the total drag for the turbulent case is considerably less than for the laminar case. So that if we are dealing with blunt objects, and if we wish to keep the drag small, we try to make the boundary layer turbulent. But with streamlined objects, there is no pressure drag. And the viscous drag constitutes the total drag. So we try to keep the boundary layer laminar. With all these facts in mind, we can now explain another experiment we did in the early part of the film. We compared the drag of a smooth ball with the drag of a slightly roughened ball at exactly the same airspeed. At low speed, the smooth ball had less drag. At higher speed, the roughened ball had less drag. As we look at them, these two spheres look almost exactly alike. But the breadth of a hair is a sizable obstacle to a boundary layer only as thin as tissue paper. So even this slight roughening may cause the boundary layer to become turbulent earlier than it would otherwise. At the lowest speeds at which we performed this experiment, the boundary layer was laminar on both spheres. Thus the point of separation was about the same for both, and both had about the same pressure drag. But roughness increases skin friction drag, so the total drag was greater for the roughened sphere. Now, what happened when we increased the speed? The boundary layer became turbulent for the roughened sphere before it did for the smooth sphere. A turbulent boundary layer remains attached longer, and so the pressure drag of the roughened sphere was considerably reduced. Reduced so much, in fact, that now the roughened sphere had less drag. At some speeds, the drag of the roughened sphere is only about a fifth the drag of the smooth sphere. You know, a long time ago, golf balls used to be smooth. Here is the kind we use today, dimpled. And here is a scaled model of it. Using the equal arm balance, we compare the drag of the dimpled ball with the drag of a smooth ball having exactly the same diameter. Over the entire range of speeds corresponding to those at which pros and duffers drive off the tee, the dimpled ball had less drag. So you see at least one good reason why golf balls are dimpled. In our explorations of the fluid dynamics of drag, together we've covered a great deal of ground. And fluid flows are complicated. But with your understanding now of the interplay among pressure forces, viscous forces, and inertial forces, with your knowledge of the Reynolds number as the most useful correlating key in this balance, with your appreciation of what a boundary layer is and how it behaves under laminar and turbulent conditions, with your grasp of all these things, you can now think intelligently about a wide variety of flows.